Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. In this video, I would like to discuss a new chapter, chapter 7. Okay, it's about ordinary differential equation, okay, with boundary value problem. And the method that we want to discuss in this video is shooting method. In ordinary differential equation, initial value problem, the condition is specified at the same value of the independent variable. But for ODE, for boundary value problem, the conditions are specified at different values of the independent variables. So here is the general form of ODE for boundary value problem. Mostly, ODE with boundary value problem are very hard to solve analytically because of the equations are very complex. Hence, the other option to solve the ODE with BVP is by using numerical methods. There are two methods that can be solved by using numerical. The first one is a shooting method and the second one is a finite difference method. In this video, okay, we are going to discuss about the first method. That one is a shooting method. Okay, shooting method is a technique of converting the boundary value problem to an equivalent initial value problem. Then an initial value problem is solved via a trial and error approach. This technique is called a shooting method by analogy to the procedure of shooting the object at a stationary target. Here are the steps how to solve for shooting method. Okay, the first step, reduce the second order boundary value problem of equation to a system of first order initial value problem. The second order ODE is transformed into a system of two first order ODE as shown below. Step number 2, okay, determine the initial value. The boundary value at the first point of the domain is known and is used as one initial value of the system. The additional initial value that required for solving the system is guess. The next step, step number 3, the equivalent system of initial value problem is then solved via Euler method, RK2 method, or can be solved by using RK4 method. But in this course, okay, we just consider for Euler method only. Then the next step, step number 4, the solution obtained at the endpoint of the domain is compared with the boundary condition. If the numerical solution is differ from the boundary condition, then the guess initial value is changed and the system is solved again. Okay, last but not least, step number 5, if the result obtained from the second initial guess also differ from the boundary conditions, then we need to extrapolate the initial value by using linear extrapolate formula. So this is the formula where G1 is the first guess at initial slope, G2 second guess at initial slope, R1 final result at endpoint using our G1, R2 second result at endpoint using our G2, and the last one D is the desired value at the endpoint. Okay, after we have our new guess, okay, then the system again is solved by using Euler method. For better understanding, let's try one example. The position x of a falling object at time t is governed by this equation with boundary conditions x0 equal to 0 and x20 equal to 800. Approximate the solution of the position x for each interior nodes by using a linear shooting method. Use the first initial guess z0 equal to 5 and the second initial guess z0 equal to -5 and our step size equal to 5. Okay, so let's go to the solution. So first step, okay, let's rearrange our equation into our general form. So let's move 2 to the other sides. Okay, so the equation become 4.9 minus dx dt. Okay, so this already in our general form. And then let's change from second order to first order. Okay, so first step, okay, let dx over dt is equal to z. Then we differentiate again, so we will have d square x dt square is equal to dz over dt. And d square x dt square is here. 4.9 minus dx dt is equal to z. Okay, so from here we have two equations. So the first one will be our F1 and the second one will be our F2. Okay, then let's sketch our timeline. Okay, so we start with T0 is equal to 0 and the increment is equal to 5. So we have T1 is equal to 5, T2 is equal to 10, T3 is equal to 15, and T4 is equal to 20. Okay, and if t equal to 0, we have x is equal to 0, so x naught equal to 0. And then the next one, when t is equal to 20, we have x is equal to 800, so x4 is equal to 800. So we are going to find the value for x1, x2, x3. Since, okay, we have two differential equation here, that's mean with three variable x, z, and t. So we need to solve by using system. By using system of Euler, so the formula, okay, so we have xi plus 1 is equal to xi plus f1 ti xi zi multiply with h. And then we have zi plus 1 is equal to zi plus f2 ti xi zi multiply with h. And the last one, ti plus 1 is equal to ti plus h. So this is the formula of Euler for system. Now let's start our calculation. So firstly, make sure you know when t is equal to 20, our x must be 800. So for the first calculation, let's start with our first initial guess. Z0 is equal to 5. So we solve our problem by using system Euler for system, and I present my answer in this table. And if we see when t equal to 20, our x is 72.5. This is far away from our condition. So we need to proceed to the next calculation where the second, we use the second initial guess where our z0 is equal to minus 5. Again, we solve our problem by using Euler for system, and I present my answer in this table. And when t is equal to 20, this is my x, where my x is over from our condition. Okay, because of that, okay, we need to use linear extrapolate to find the new initial guess. But before that, okay, I just want to tell you that our z0 is equal to 5. This will be our g1. And our second z0 is equal to minus 5. This is will be our g2. And answer from the first calculation here, 72.5, this is our R1. And answer from the second calculation, this will be our R2. So this is the formula for linear extrapolate. So let's substitute all the information that we have. So we start with G1 is equal to 5 plus, okay, G2 minus G1, that's mean minus 5 divide by R2 minus R1. So we have 2622.5 minus 72.5 multiply with D minus R1. So we have 800 minus 72.5. So just by using our calculator, so our new initial guess, Z0 is equal to 2.1471. So continue our calculation by using the new initial guess. Z0 is equal to 2.1471, and solving the same problem by using a system of Euler, and I present my answer in this table. So now I have when t is equal to 20, my x is 799.98695, where this one is near to 800. I hope you can understand all the explanation, and please try your best. Okay, so thank you. See you in the next video.